Hi, and thanks for tuning in. My name is Igor Izatov. I'm an enterprise solution architect with AWS based in Sydney, Australia. I support financial services customers, helping them move and modernize their workloads on AWS. It should come as no surprise that the majority of these workloads involve databases in one way or another. For this session, I have collated some of the patterns for seamlessly integrating AWS managed databases with other cloud services to enable analytics, increase resiliency, and operational excellence. I'm using the word seamless here not as a cliche. Most patterns I cover in this session require little or no modification to your application. This is a level 300 session, and I'm assuming you have a working knowledge of AWS. Let's get stuck in. Moving workloads to AWS at an enterprise scale is a journey that can be represented as a series of steps, with each step unlocking additional benefits. You can choose to follow them linearly or fast-track your journey in accordance with your organizational cloud maturity. As a first step, you can choose to rehost application infrastructure to the cloud as is to gain agility, elasticity, and reduce capital expenditures, such as database license fees. To automate the undifferentiated heavy lifting of database administration, you can adopt managed services, such as AWS databases. This step is also known as replatforming. Or you can choose to refactor your application if you are in a position to modify the application code and architecture. We generally see customers adopt a microservices-based approach, with each microservice running on top of a purpose-built data store, which is markedly different to the traditional relational database for everything approach. Let's now talk about purpose-built databases on AWS and refactoring in more detail. AWS offers a selection of managed database engines for you to choose from based on the use case, access pattern, performance, and scale requirements. The first and the most popular category is relational, for workloads requiring strong consistency and schema, such as a core banking platform or an ERP system. This is where Amazon Aurora fits alongside Amazon RDS with open source and commercial database engines. Today, I will focus on this category. In the non-relational category, we have Amazon DynamoDB and MongoDB-compatible DocumentDB. These databases allow developers to store and query key value and JSON documents. As an example, you may consider going non-relational for a high-traffic gaming application that can tolerate eventual consistency. Other database categories include in-memory, graph, time series, ledger, and wide column. You may choose those for IoT, social networking, industrial telemetry, and supply chain scenarios, respectively. Airbnb is a great customer example that demonstrates the use of purpose-built databases. Airbnb uses DynamoDB for storing user search history and hyper-personalization. DynamoDB is a great fit here, owing to its horizontal scalability and guaranteed low-latency query performance at any scale. Elasticache, with its in-memory performance and sub-millisecond response time, makes it a perfect option for storing user session state across all of Airbnb channels. For financial transactions and bookings, Airbnb uses AWS relational databases because of their strong consistency and referential integrity. But Airbnb is a born-in-the-cloud company that could design their applications for the cloud. This is not always the case with traditional enterprise applications designed to run on premises. Let's discuss how AWS can help you with refactoring those. As I mentioned before, refactoring allows you to make the most out of your move to AWS. But it often is the most demanding migration strategy, both in terms of engineering maturity and in terms of effort. Now, imagine a situation where you have a SQL Server-based application that contains T-SQL, good old triggers, stored procedures, and so on. And this application connects to SQL Server over TDS, SQL Server's wire protocol. We assume that your refactored application will still require a relational data store, and we recommend you use Amazon Aurora, our cloud-native Postgres and MySQL-compatible database. To help you with database schema conversion and data migration, we have tools like AWS Schema Conversion Tool and AWS Database Migration Service, or DMS. But up until now, rewriting all that application code and in-database T-SQL was entirely on you. And we know it's not an easy task. This is the reason why we built Babelfish for Aurora Postgres. Babelfish is a new translation layer for Aurora, making Aurora understand queries from applications written for Microsoft SQL Server. In other words, your application can run directly on Aurora with little or no code changes. Babelfish is generally available for production use today. Let's use the magic of PowerPoint animations to demonstrate it. Let's move the SQL Server application stack over to the side for a moment. Now, if you turn on Babelfish in Aurora, it will expose a SQL Server compatible endpoint. Now, we can bring the application back into the picture and connect it directly to Aurora. Your legacy application code can remain written for SQL Server and does not need to be changed. Furthermore, you can write new application code for Postgres, running it side by side with your legacy code for SQL Server. We decided to make Babelfish an open source project, and it's available on GitHub. We wanted to give you complete transparency into its roadmap and enable you to make your own modifications and extensions to this translation layer. Now, let's talk about other architectural patterns to make the most out of your move to AWS relational databases. Let's first talk about architectural patterns that can help you with analytics and machine learning. The patterns I'll be discussing today form a part of what we call the modern data architecture. Modern data architecture proposes a set of principles to enable unified governance and easy data movement in order to enable various analytical use cases, such as data warehousing, operational analytics, data lakes, streaming analytics, as well as AI and machine learning. Historically, analytics was the domain of data warehouses and ETL processes that extracted data from source databases, transformed and loaded into rigid schemas such as Data Vault or Star Schema. More recently, organizations started building data lakes in order to load data from sources quicker and to be able to run diverse analytical workloads directly on top of a common data repository. In order to support specialized use cases, customers began using specialized data stores, such as NoSQL databases, OpenSearch clusters, or cloud-native data warehouses. The challenge with this approach was the growing complexity of data movement in and out of the data lake and between these data stores, especially as the volume and diversity of data kept growing. Modern data architecture seeks to address this challenge by integrating a data lake, a data warehouse, and other purpose-built data stores while enabling unified governance and seamless data movement. Modern data architecture is enabled through tight native integrations between AWS operational data stores and various analytical engines. Let's explore these integrations in more detail. Businesses can no longer afford to wait for an overnight data movement to complete. The world is moving towards intraday and real-time decisioning. The first pattern allows you to seamlessly combine historic and operational datasets without ETL, enabling you to make decisions quicker. Using Amazon Redshift and Amazon Athena Federated Query, you can run analytical queries combining real-time data in RDS or Aurora with historic data in Redshift or S3. Some customers standardize their data architectures using streaming patterns. And on AWS, you can stream changes directly out of your relational databases to S3 using change data capture in AWS DMS. Data landing in S3 can also be queried in place by Redshift Spectrum or Athena. If you need to perform transformations or publish this stream of changes to other systems, you can use DMS together with Amazon Managed Streaming for Kafka. Kafka in this case becomes a durable log that can be independently processed in near real time using frameworks such as Spark. For infrequently changing data, you can continue to update your data lake or data warehouse hourly or daily. Open source Postgres, MySQL, and MariaDB databases on AWS support exporting database snapshots to S3. When you export a database snapshot, its contents will be loaded to S3 as compressed and query-optimized Apache Parquet format. You guessed it, these snapshot extracts can also be queried in place using Amazon Athena or Amazon Redshift Spectrum. To democratize machine learning, Aurora integrates with Amazon SageMaker and Amazon Comprehend to perform predictions or inferences. For example, you can enrich operational data in Aurora in real time by natively calling SageMaker models for scenarios such as fraud detection and product recommendations. Using a simple SQL query, you can pass a customer profile and their shopping history to a SageMaker model and retrieve inferences as query results. Similarly, you can use Amazon Comprehend to uncover insights and connections in text, and, for example, analyze customer sentiment or categorize and route inbound support requests. The last group of patterns simplifies data movement between disparate sources. If you are using Postgres, you can use Postgres Foreign Data Wrappers, or FDW, to retrieve data from a remote source. Since Redshift exposes a Postgres-compatible query endpoint, you can use FDW to enrich data in your applications with insights from your analytical data marts without building complex data movement logic. You can also use foreign data wrappers to query data from external databases, including those running on premises and EC2. When the data resides across heterogeneous data stores, you can use Glue Elastic Views, a service that creates a virtual table or a materialized view, which combines data from across a variety of data sources using familiar SQL. Glue Elastic Views does not only copy data from source databases to a target database, it also monitors sources for changes and automatically updates the target within seconds. You can also use Glue Elastic Views to hydrate your data lake in near real time. Hopefully I've been able to demonstrate how RDS and Aurora natively integrates with S3, Redshift, Athena, SageMaker, Comprehend, and Glue to simplify data movement and enable a variety of analytical use cases as part of the modern data architecture. Let's move on to the next topic, reliability. Reliability is the quality of a system to remain functional, and it largely depends on resiliency. Resiliency is the ability to recover from infrastructure service disruptions, dynamically acquire computing resources to meet demand, and mitigate disruptions such as a misconfiguration or a transient network issue. Since we're on the topic of AWS managed databases today, it's important to note that reliability also includes the ability to retain and recover data when failures occur at a data store level. Let's first look at some of the common enterprise reliability challenges to set the scene better for reliability patterns. Historically, many enterprise customers have designed their software development life cycles and operations around infrequent releases. Biannual or quarterly releases are usually big changes that require months to prepare and execute. One of the problems with big changes is that they're usually hard to test end to end, and this lack of test coverage makes them more prone to reliability issues. And due to their size, they're also harder to roll back in case of a failure. Ongoing resiliency assurance are usually big annual exercises too. We commonly see organizations update their runbooks and recovery processes leading up to these drills. But since the business does not stop, a once-a-year test is usually a week-forcing function to ensure that the operational procedures remain up to date throughout the rest of the year. Another challenge is the tendency for systems to get more complex over time. You may start with a well-tested system, but over time, as systems and their dependencies evolve, the impact of failures becomes blurry and poorly understood. And finally, as your own company grows, so does its internal operational complexity. This may lead to fragmentation in enterprise monitoring tools across infrastructure, database, and application layers. All of the above-mentioned challenges may negatively affect your ability to detect failure and recover quickly. Let's look at some of the recent AWS innovations in this space that you can adopt to increase reliability of your workloads in the cloud. Let's talk serverless databases first. Traditional databases scaling mechanisms take time and may affect your in-flight queries. It may sound as a surprise, but serverless databases, such as Amazon Aurora Serverless, can help avoid load-induced failures, especially when your workload is spiky and unpredictable. With serverless computing, infrastructure management tasks like capacity provisioning and scaling are handled by AWS transparently, so you can focus on writing code that serves your customers instead of database sizing and scaling. The initial Aurora Serverless v1 offering was a good fit for dev test workloads. Aurora Serverless version 2, which has recently been promoted to general availability, moves the needle further into the territory of high availability and reliability. It offers full feature parity with Aurora provisioned, and it even supports hybrid scenarios, enabling you to mix provisioned with serverless in one Aurora cluster for rapid scalability. For example, if you are dealing with a read-heavy, spiky workload, you can provision an Aurora Serverless read replica that will scale dynamically, absorbing the load and reducing the risk of resource starvation, which may lead to a denial of service or a failure. We're beginning to see customers embrace serverless architectures as a standard within their organizations because it eliminates operational overhead, lowers costs, and enables them to move from idea to market faster. Testing the resiliency of your application should not be a once-off exercise, especially if you're making frequent changes. We recommend to make resiliency assurance a part of your software development lifecycle in order to continuously understand the reliability posture of your application as it evolves. If you are using Aurora, you can continuously test your application by performing high availability, stress, and volume testing on the database layer. These tests can be triggered by running simple SQL commands. For example, you can test how your application will recover from a database engine crash by interrupting an Aurora node. You can stress test your application by disrupting a percentage of requests on Aurora read replicas, or disrupt Aurora attached storage. You can also verify how your application reacts to increased read and write latencies by simulating congestion on Aurora's storage. These mechanisms allow you to observe how your application responds to these events and make your code more resilient and therefore reliable. By simulating real-world conditions, you can uncover latent bugs, monitoring blind spots, and performance bottlenecks, all of which are notoriously difficult to pinpoint in complex systems. Using AWS Fault Injection Simulator, or FIS, you can orchestrate fault injection scenarios across all parts of your application stack, not just the database. For example, you can codify a concurrent interruption of a number of EC2 instances, simulate network partitioning, security group misconfigurations, force database failovers, and so on. FIS will help you run these experiments regularly and collect valuable telemetry that you can use to improve reliability of all the components of your application. There are some good customer stories on this topic from the internet. For example, Netflix define resiliency goals and continuously test their systems by injecting chaos directly into production. I encourage you to read more about it on the Netflix tech blog. If you are migrating from on-premises, you would be familiar with a traditional enterprise recovery model, usually involving a primary and a DR location. Failover process is usually complex and is invoked when recovery within the maximum allowable outage is not feasible. Each AWS region includes at least 3 availability zones, or AZs, and all AWS managed databases offer multi-zonal resiliency and recovery capabilities. We believe that for the vast majority of workloads, the highly resilient regional design of AWS is the best way to achieve availability goals. For example, this is how Amazon.com has run and still runs today. Customers with very high availability requirements, for example, nationally critical services or payment systems, can choose to deploy across 2 or more AWS regions to achieve further resiliency against an extremely unlikely event of a full AWS region impairment. In most cases, to achieve this deployment pattern, the workload has to be specifically designed to run across multiple AWS regions, and it requires a deep understanding of its dependencies, failure modes, trade-offs, and impacts of asynchronous data replication. In the next slide, I will walk you through some of the cross-regional resiliency and recovery patterns for databases. If you are considering a multi-region deployment model, please engage your AWS Solutions Architect to validate your approach. Let's look at Amazon Aurora first. In addition to being multi-AZ by design, Aurora Global Database can replicate to other AWS regions. You are in full control of choosing which regions to replicate to. For example, if your data cannot leave Australia, you can enable replication to the upcoming Melbourne region. Adding more AWS regions can help reduce latency for geo-distributed read-only workloads and help increase your application's reliability. One of the secondary regions in the Aurora Global Database cluster can be promoted to read and write capabilities quickly, achieving a single-digit second recovery point objective. Mature customers may architect their systems using the follow-the-sun model, whereby the primary writable database fails over from one AWS region to another multiple times a day, following the peak of customer activity. This advanced approach helps embed reliability engineering practices and enables continuous assurance and measurement of resiliency. Keep in mind that AWS regions are geographically separated, which means that cross-region replication is sequentially consistent and asynchronous. In the case of Aurora, it happens at the storage level with no impact to database performance. It leverages the AWS global network, achieving predictable sub-second replication latency. Furthermore, with Aurora Postgres, you can define an RPO target for global replication, and the engine will monitor the replication lag across all secondary clusters, ensuring that at least one secondary cluster stays within the RPO window. This helps ensure that in the case of a regional failover, the amount of potential data loss remains below the specified threshold. Aurora Global Database is not the only pattern you can use to achieve multi-region resiliency. You can use DMS and change data capture to continuously ship database transactions across 2 AWS regions. Some customers use this approach to save on database license costs. For example, using RDS for Microsoft SQL Server Standard Edition instead of Enterprise Edition. What's interesting about this approach is that you can be selective about tables that you replicate and create bounded replication contexts. DMS also supports bidirectional replication for more advanced architectures involving regional data sharding. Please keep in mind that bidirectional replication in DMS is not intended as a full multi-master solution with conflict resolution. Another option is to use RDS read replicas in a different AWS region. A cross-region replica can be promoted to primary with read-write capabilities as part of disaster recovery, and this capability is supported in all RDS engines except SQL Server, for which you can use the DMS approach. Open source engines such as MariaDB, MySQL, and Postgres also support logical replication that can span AWS regions. Logical replication offers more flexibility when it comes to defining replication topologies. For example, the Postgres PG logical extension supports row and column filters. Again, these replication topologies can be multi-way, enabling you to build interesting horizontal and vertical sharding patterns across multiple AWS regions, helping you architect workloads using bounded contexts to minimize the blast radius. One thing worth noting here is that logical replication does impact database performance. Please make sure to conduct performance testing to understand the impact in your particular case. Now it's time to move on to the last topic of today's session, operational excellence patterns with AWS databases. Operational excellence forms a separate pillar of the AWS well-architected framework. It covers how your organization supports its business objectives, runs workloads efficiently, gains insights into operations, and continuously improves supporting processes and procedures in order to deliver business value. There are 5 design principles for operational excellence in the cloud that all have a direct impact on reliability and recoverability. Perform operations as code, or in other words, define your entire workload as code and update it with code. Make changes in small increments that can be quickly reversed if they fail. Update your runbooks and operational procedures as you evolve your workloads. Don't delay or defer it. Test your failure scenarios and validate your understanding of failure impacts by using fault injection and by running regular game days. Lastly, drive improvement through lessons learned from all operational events and failures and share those lessons throughout the organization. This is an important feedback loop that helps you improve over time. Telemetry and observability are key to achieving operational excellence. AWS databases natively integrate with Amazon CloudWatch, delivering a real-time stream of database logs and metrics. You can automate detection of and response to certain conditions or anomalies, such as database deadlocks or resource starvation, ideally way before your customers feel the impact, by using AWS Lambda integration with CloudWatch alerts, log event filters, and CloudWatch anomaly detection. You can start simple by auto-cutting internal support tickets and grow towards high degrees of automation, such as invoking programmatic responses to situations like anomalous database memory consumption or errors in database logs caused by bad queries. Sometimes you need to take it up a notch and have a mechanism for real-time query auditing to be able to detect failing, anomalous, or even malicious queries, or to help safeguard your critical databases and meet compliance and regulatory requirements. To help achieve that, RDS and Aurora natively support database activity streams, a feature that pushes all database activity to an Amazon Kinesis data stream in near real time. From Kinesis, you can trigger Lambda or feed the activity stream to a third-party security solution for inspection, auditing, and, if necessary, real-time intervention. Lastly, I want to touch on a feature available in all RDS and Aurora open source database engines that enables a native event-driven integration between a relational database and Lambda. Functionally, it's as simple as creating a database trigger that makes a synchronous or asynchronous call to Lambda. Customers use this capability to build interesting integrations, for example, pushing out data to SQS or DynamoDB. But for the purposes of operational excellence, this feature can be adopted to verify if certain DDL or DML operations have been authorized as part of your change management process and blocked if necessary. Lambda integration may introduce a performance overhead, so please ensure to performance test your solution. I spoke earlier about a recommendation to make small incremental changes that can be quickly reversed if they fail. Historically, it's not always been straightforward with relational databases, especially when breaking schema changes are involved. With Aurora Fast Cloning, you can create a clone of an Aurora cluster containing all its data in seconds, regardless of your database size. Aurora leverages a copy and write protocol, and initially both databases reference common pages on the Aurora shared storage, therefore making it a logical operation without physical data movement. Because Aurora clones are isolated writable Aurora instances, you can make release changes and promote them to production as part of your release process. Rollback becomes as easy as reverting to an old Aurora instance. Companies also use Aurora fast cloning to refresh development environments and to isolate work on specific application features. This also includes the ability to test performance impact of each new feature in an isolated production-like environment against a full dataset, helping to increase release quality and reduce rework and rollbacks. We also see customers use Aurora fast cloning to perform complex maintenance tasks on an isolated database clone before promoting it to production. These are only a few patterns that you can use with Aurora fast cloning. I'm looking forward to learning how you make the most of this capability in your organization. We're at the finishing line. As next steps, I recommend reviewing the Airbnb case study and getting your hands dirty with Amazon Aurora Labs and our disaster recovery workshop. I also encourage you to experiment with Aurora Serverless v2 to see how it can help increase responsiveness and availability of your workload. And as always, if you have any questions, please do not hesitate to reach out to your AWS solution architect. To continue your cloud journey, please use these training resources from AWS Training and Certification. I thank you for tuning in, and I sincerely hope you found this session useful. We really value your feedback. It helps us improve our sessions, so please do not forget to complete the session survey.